What's up, everyone? I am Niranjan Krishna. So, this is part of a new series called Machine Learning from Scratch, where we basically implement machine learning without the use of external libraries, external machine learning libraries. We may need to use libraries like NumPy or Random, but that's it. Alright, we don't use TensorFlow, Keras, Theano, Pytorch, etc. All these libraries. So today's linear regression. Okay, yeah. So linear regression is basically predicting an output value given an input value after training on similar patterns. So let's say we want to create a program that will predict the double of a number, that will double an input, let's say we give an input x and it will double it as the output. So we want to make such a program. Let's say we are giving 2 and the output should be 4 because 2 into 2 is 4. Well, first thing the network does is initialize these random variables w and b, and w is multiplied to 2 and b is added. Basically what these variables do is they are randomly initialized. So let's say w is 1, alright, w is 1 and b is, let's say, 2, alright. So not 2 is really bad. Okay, b is 3. So the result is 5, which is certainly not equal to 4. So we got a prediction, right? And then what in linear regression what we do is we calculate the error. So the error, a simple error function would be the actual value minus the predicted value. So we calculate the error, and the error turns out to be -1. So we get this error. And by the way, the prerequisite for this series is linear algebra, calculus, probability, some statistics, and make sure that you are comfortable with Python syntax, because we are going to be doing it in Python, right? So we have -1 as the error. Then we do what I call back propagation through time. Basically we calculate the local minimum of a particular variable in a function. How that variable can be adjusted, can be changed, so that the function with respect to that variable, but by changing that variable, the function's value will be lower. And since this is an error function, we want the error to be low. And see, the problem with this output minus predicted error function is that since we want this error to be low, when the network sees -1, it will think that it's doing a good job, so it will move on to like really negative values. And this, what is this, why is this? Okay, don't worry. And it will go to like big, the prediction will be big values, so that the error will be negative, so that the loss is less than 0. So this is not a good example of an error function. That's why we used mean squared error, which is basically output minus predicted squared, so that the error function always means positive. So I don't think you got a lot of idea from that. Let's code it out. We'll go as we're coding. Alright. So I have my Jupyter notebook right here. So first I'm going to import NumPy, then I'm going to import random. I'm just going to save it just in case. Where's the save? Okay, this is save. Alright. Then next I am going to create the next x. It's an array of all the points 2, 4, 6, 8, 10. See, and we have y, which is basically the double of these inputs. So 4, 8, 12, 16, 20. Alright. So we have these two. Then we have our weight. So weight is going to be random.random. It's going to be a random float. And bias is going to be random.random. Alright. So as I said, we are initializing the variables right here. Next we are going to be doing like forward propagation. Alright. So what forward propagation does is that, let's give it parameters. Let's say the input, the weight, the bias, input not input, let's say x. Okay, x. This is nice. So what forward propagation does is it basically multiplies the input value by w and adds a bias to it so that it has a prediction. So say prediction is equal to weight times x plus b bias, and let's return the prediction. Now we're going to try it. Forward propagation of say x dot x, the zeroth element. Can you say zeroth? I don't think. The zero element, you get what I'm saying, right? Zero element of x and the w and b, which is a weight and bias. So I'm gonna print that prediction. Let's run it. So it actually printed 2.410, which is, yeah, I'm gonna print the w and b so that we can be more clear on that. Okay, let's see, like this. So w right now is 0.3 and the bias is 0.1. So 0.3 into 2 plus 0.1 gets a prediction score of 0.7. That's forward propagation. That is way off the margin. I'm gonna show you how to eradicate that. So let's say def train. So this is the function train, and in it we are gonna give the input array, the output array, the weight and the bias. These are the inputs. And there is another thing called the learning rate. If you checked out any articles on machine learning, I'm sure you know what learning rate is. Learning rate is basically, think of it like this. Okay, yeah, wait a minute, I will explain that during back propagation. That will be better. So learning rate, I'm going to initialize to value equals 0.01. Okay, all right. Now then we have epochs, which is basically training iteration. This is all going to make sense when I explain the back propagation part. Let's say for 100 epochs. Now I'm gonna put, let's get the function. If I don't talk about back propagation, none of this will make sense. Propagation, all right. So x and y, no, y prediction, x weight and a bias. Okay. Oh, wait a second. Okay, error function. Okay, after this prediction, turn prediction squared. Right. Okay, we are done. Okay, let's say we have a function. I'm gonna say we have a function w into x plus b. So we have this function and it predicts a value. Let's call it y prediction, but there is the actual value which is y, right? So we want to fine tune, we want to fine tune w and b such that yp can get more closer and closer to y. So what do? First we calculate an error function. So in this case it is mean squared error squared. All right. What does this set? Suppose if yp's, y predictions value is near to y, the error will be really small, else the error will be really large. And remember, the yp function is basically w into x plus b. Let me just draw the brackets here. All right. Oh, okay. This is basically the error function. What the error function basically is. So what we are going to do now is we are going to fine tune w such that when it is fine tuned, it will be a new value such that that will cause the error to decrease. So we are decreasing the error function with respect to w. So we are basically finding the local minima of a function with respect to a particular variable. That is by using a gradient or by simply taking the derivative of the weight in that particular function. Derivative of the, let's just let me just get the eraser a little bit. Okay, let's I think I got a resize. Let's say, oh, only 500. Okay. Come on. Yes. Okay, that's pretty good. Yeah, that's good. So we got a loss function. Oh, not a pencil. I don't want a pencil. Okay, this is better. Loss function is equal to y minus w into x plus b whole square. All right, this is our loss function. Now, how do we take the derivative with respect to w here? This is known as a partial derivative. So, if you are familiar with calculus, I am pretty sure you guys know how to take a derivative using the chain rule. So, this, let's say that y minus w x plus b is a function u. So, according to the chain rule, that would be derivation of the loss function with respect to derivation of u into derivative of u with respect to derivative of v. See, the du part in this cancels out, and it's actually the derivative of the loss function with respect to the variable w. All right, let's go. So, if it is u, which is equal to 2 into u by derivative of u with respect to w, right? So, since u is y minus w into x plus b, this is the function. Now, since this is a constant, the derivative of a constant is 0. So, it is 2u into negative of, okay, I don't know how Khan Academy does this. This is so hard. All right, we got it. Okay, so remember u is y minus wx plus b. Okay, so now the derivative of wx is going to be well, x, because this is w raised to 1. So whenever we are taking a derivative of a particular variable, variable with exponents, we are going to take the constant out. So in this case, x is treated as a constant according to the partial derivative. So x is taken out, and since this is w raised to 1, 1 is taken to the left, and I am going to illustrate the chain rule. Right? The chain rule basically states that derivative of a function x raised to n is basically n into x raised to n minus 1. According to that logic, the derivative should be 1 of w, because n minus 1 where n is 1 is w raised to 0, which is just 1. So, the constant is going to be left standing, so x. So, we know that derivative of the loss function with respect to w is going to be x. And see, I have not considered b because it is a constant, and the derivative of a constant with respect to a variable is just going to be 0. So, let us take b now. Following the same rules, okay, wait a minute, the derivative of the loss function with respect to w is not just x, it is going to be, here there is a negative. So, it's going to be negative x negative 2xu. That's going to be the derivative. So following a similar fraction, we know negative 2u is going to come. Then we have to take the derivative with respect to bias of wx plus b. W and x are treated as constant here as according to the partial derivative, and b is taken. As I have said, using the chain rule, the derivative ends up being 2u into 1, 2u into 1. So, negative 2 into 1, which is basically negative 2u. So, now that we know the derivatives of w and v, let us go to back propagation. Okay. And what back propagation basically does is that by taking these derivatives, it subtracts the derivatives from the actual weight, right? It subtracts it from the actual weight, and this causes the weight to move a little bit towards the local minima of the weight in the particular function. And also, I haven't explained when we are doing this a couple of times, let's say for 100 times, it moves closer and closer towards the local minimum. And why the learning rate factor here is basically because let's think about it. Imagine you are a tourist and you are visiting Paris. So you want to find the Eiffel Tower, and there are a lot of crossroads. You are starting from a point. Let's say you are starting from here, and Eiffel Tower is here. So you are seeing a lot of roads like this and this, and assume this road right here leads to the Eiffel Tower. My Eiffel Tower looks like a, forgive that. So you asked a person where to go, and they say there is a road with a particular sign. Let's say this is the sign. You have to look for that sign, and wherever the sign falls, that will be the road towards Eiffel Tower. So you start walking. Let's assume you take 20 steps at a time. Okay, so this covers a distance. This is the distance between each road is 10. This is 10. This is 10, and this is 10. Let's assume you cover 30 steps at a time. So at the first time you're gonna be here, right? Then you are thinking, oh, I might have gotten too far, let me go back. So when you go back a little bit, you see the signal right here, the road. So you understand that it is the road which leads to Eiffel Tower. You go there. But instead, think about this. Assume you are only taking 10 steps at a time. So you are taking the first 10 step, you are taking the second 10 step, and you are saying, oh, I got the road, I am going to Eiffel Tower now. So in the second example, you reach the Eiffel Tower far more fast. So what essentially learning rate does is that it upgrades these derivatives by a small margin such that we can effectively find the local minimum of a function. So let's implement it. Okay, so we have the error function y minus prediction squared. Now back propagation. So we know back propagation is going to be weight. We have to subtract the gradient, all right? We have to subtract it into 2 into y. Okay, y minus prediction and just into x, small x, yes, and we have to multiply it by negative 1 as we saw in that example. It's equal to negative 1 into 2 into y minus predict. Okay, we have the weight and bias right now, and let's calculate the error to error. It's going to be error of y and prediction. Alright, let's call it loss. I don't want to use the same name for variable and functions, just creeps me out. It's one of my pet peeves. So return error, weight and bias here. So we have already taken the derivative. Now let's code the training function. So what we do is we repeat this process for the number of epochs, or basically iteration. We repeat this a lot of times, epochs, and for every single index, every single input data. So we gonna say length of x. So and then we're gonna say prediction is equal to forward propagation of what? X, jth element of x and weight and by, so no, it's w and b, right? Okay, w and b. Next we're going to say error and w and b. So we are updating the weight and bias, and back propagation of y, okay, y, the jth element of y, the prediction, the jth element of x, the w value, b value, and we have to add the learning rate argument. Let's add the learning rate and let's multiply. So this gradient is multiplied by the learning rate, right? So it's multiplied by the learning rate. Okay, next, so I'm gonna print it every single time. So I'm gonna say error and let's print. Okay, I don't need the weight and bias, so I'm just gonna print the error, and I am gonna print what is called the batch size, which is at which particular set of input data are we in. So batch size or batch number is gonna be string of the j, all right, and add this to, okay, this. And then here I'm gonna print epoch plus string of I, and at last here, okay, wait a minute, I am gonna add an argument here called error is equal to 0 and error plus equal to error. So we are basically adding all the error, and the end of it we're gonna print average error plus string of the error divided by length of x, because we are basically taking the average. Then I'm gonna, no, I don't need to initialize the error to 0. So yes, so that is done, I guess. So train x comma y comma w comma b comma learning rate comma epochs. Let's run it. Okay, there is something wrong with it. Oh, all right, what is wrong? And what where 30th line? Yeah, I got it. Okay, yeah. So we have the function error, and yeah, gotta change the name. Say loss is much better. Error is a function's name, alright. Loss is much better. Yeah, now let's run it again. What? I saved it. No, not this. This. What's the problem? Where in 30 again. Loss is in the function, right? Yes, loss of function. Let me see. Like, what is the problem right here? I can't seem to figure it out. Error of I and prediction. Oh yeah, I got it. Because we are basically returning a function. All right, this is better. So now see, we are training. So first the average error is 19 and it reduced to 0.13. It's reducing each time step. It's 0.1817. At last, what is the error? 0.057 by 100th epoch. Oh, why did I open Opera? I don't like Opera that much. Yeah. So I'm gonna print W and B after this. This, let's say 1,000 times. Let's see what happens. So yeah, it is computing. It's computing for 1,000 times. Oh, it is pretty fast. It's just linear regression. Okay, so the average error is 1.29. I don't even know what that is. It's so low. Look at this, 0.00. Yeah, the point is it's really low. Let's test it out. So we are taking the prediction will be, let's take an input value. Let's put x is equal to 2 here into x plus this would be a small value, and let's print our prediction. And I'm gonna print the rounded value of our prediction as well. Let's just run it. So it's 4. The rounded value is 4. Let's say it's 10. 20. Okay, this is not bad. Let's and there is this concept where our data is not from the training set. Let's give it entirely new data. Let's say 15, not too far from the what we gave in the training set. So 15, it is 30, right? So we have successfully done this example. Wait a minute, let me look at the time. So it has been 27 minutes. So yeah, not bad. So
Yeah, so that's it for today. Tomorrow I'm going to, not tomorrow, well, soon I'm going to show you how to implement logistic regression in Python without using machine learning libraries, essentially binary classification of numerical data. So wait for that video. Until that time, see you. Bye.